Hey guys, sorry about this morning. So if you got up early to do that Google Meet and then I canceled kind of last minute, like 15 minutes before, I apologize. Just had stuff going on this morning. I thought I could do a whole bunch of stuff and then still have Google Meet, but didn't have time. So I apologize. Um, so we will have one Monday at 9:30. I'll post this video and then I'll also send you guys a message through the classroom and maybe through Remind as well. But so anyways, I'll see hopefully all of you Monday at 9:30. But here's what I want to do. I'm going to go over the work that was due today, just some Regents practice problems. And then we're basically done with solutions. And I want to get into some more math type stuff that you would use in chemistry, especially those of you who want to take AP Chem. The math is important, so I definitely want to make sure I get through that. So anyways, that'll be the next thing. So I'll go over the answers to this and then take 5 minutes or so to start talking about stoichiometry. Will be the next thing we do. And then we'll just pick up with that next week. So, all right, here we go. So let's see. We had numbers 19, 20. Okay, so here we go. 19 and 20. All right, so 19. Which term represents intermolecular force in a sample of water? So, you know what? Actually, I like writing on it. So, here we go. So, intermolecular force in water. So, as we've seen before, water is attracted to water using hydrogen bonds, right? So the H of one and the oxygen of the other is partial negative, partial positive. Water is polar. The dipole moment's going towards the oxygen. All this stuff should be reviewed. So there's our hydrogen bonding. So that is number one. There it is right there. Funny little side note here. I was doing some science with my daughter yesterday, and I was showing her how you could put like 70 drops of water on top of a penny and it bubbles up, and she wasn't that interested actually, but I was trying to teach her this concept here, how water is special and is held together with a unique force. That's why it bubbles up and other liquids don't do that. And I didn't have another liquid to put on top of the penny. I probably could have found something but to compare, but anyways, she's only 4. We're getting there. Anyways, hydrogen bonding is a force. And now intermolecular is this, between two molecules. So 2, 3, and 4 are all intra, right? So if you have a water molecule, this chemical bond is covalent bonding. Metallic bond is in any metal, right? So if you have, let's say a piece of copper, right? So you got copper. So you got Cu plus 2, Cu plus 2. These are the fixed metal cations. Cu plus 2, and then you have the C of electrons around it, right? So that's metallic, and then ionic would be like salt, right? Na plus, Cl minus. They're attracted in a crystal structure, crystal lattice. So that's ionic. That would be. So those are all bonds. This is not a bond. It's a force of attraction. Okay. Let me just do that. All right. Let's see. I'm smudging that thing here. Sorry, guys. All right. Which sample is crystalline structure, solids? You see crystal, think solid. Crystalline structure. That's that lattice, that repeating. So like when we draw solids that look like this, they're really three-dimensional, right? So they're three-dimensional, but this would repeat over and over like a gazillion times. That's called a crystal structure, crystal lattice. So that's a solid. Particles really close together, packed together, and repeat over and over. Okay. All right. 19 and 20. Oh, I lost my picture here. Sorry. I took a picture of it so I wouldn't have to do this. I got to keep my phone awake. All right. 27, 32, 34. All right. Here's 27. I'll just leave this one. What am I doing here? Why are you not letting me zoom in? All right, whatever. I should be able to zoom in on this PDF. What's going on? Oh, there we go. Sorry. 27. Electrical conductivity of aqueous solution depends on concentration of, well, here we go again. I should just do this every time. So, The ions. Okay, electrical conductivity of an aqueous solution depends on concentration of ions. More ions, more concentration. More ions in a solution means higher concentration. We just kind of spent some time on that. And if they're floating and moving and mobile, it will conduct, right? So if you have a beaker here and a beaker here, let's say the water is the same. Obviously, this one's not. But let's just say the volume is the same. Let's say we have 1, 2, 3, 4, 5, 6 charges in here. And let's say the plus is K plus and the minus is F minus, right? So these are aqueous ions dissolved in water. Potassium fluoride. Same thing here. We have K plus, F minus, potassium fluoride, KFAQ dissolved in here. But over here, again, imagine the water is the same. I drew this pretty bad, all right? But over here, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. So over here, we have 3 times as many, right? So we have 3 positives, 3 negatives. We have 9 positives, 9 negatives. This one would have a higher concentration. So if we're running electricity through this, all right, positive, negative, terminals, let's say. So you're running electricity through this, and you got wires going in maybe. I don't know, I'm kind of doing this quick. But if you run electricity from a battery or a power source through these solutions, both will conduct because they have mobile ions. I showed you that a while ago at this point. But the more ions, the better, because there's more mobile particles for that electricity to flow through. All right, so that was that one. All right, 32, 34. 32, 34. Can I squeeze them both in here? Yeah, okay, here we go. All right, 32. This one's just kind of a memory thing. Nothing really here, no skill involved. Malleable, good conductor. That's a metal, non-metal, metalloid, metal, non-metal. So metal, platinum. PT is on the metal side of the periodic table here. Don't think I need to show this to you, but I will just to make sure I'm really doing what I need to do here. All right, so if we rotate this thing, platinum is right here. There's platinum. Okay, hydrogen's a non-metal. Silicon is a metalloid. And then what the heck was the other one? Xenon. Xenon, is not a metal. Okay. All right, so there's that. 34. Chemical name for sodium, for Na2SO3. All right, so we know it's sodium something. All right, so now we need to look up sulfite, sulfate, sulfide, and thiosulfate. So we go to table E. When I see these ites and eights, that means table E. Ide, I'll do this one first. Ide just means sulfur. So ide would be sulfur. That's S. So sodium sulfide is actually Na2S. Because Na is +1, S is -2. So Na2S. So that's not that. All right, now we'll do 4. Thiosulfate on table E. Okay. Thiosulfate. Here it is, down here. S2O3. So this is S2O3. So S2O3, that's not S2O3, that's SO3. So that's not right. This one would be Na2S2O3. That's what that would be. All right, sulfate. Sulfate. Where's sulfate? Sulfate. There it is. SO4. And while we're looking at it, sulfite is SO3. So that's the answer. SO3 because that's the formula they give us, SO3. So sodium sulfate would be Na2SO4. That's not right. So this is correct. Number 1. That is the correct formula for sodium sulfite. Okay. And 37, 39. What happened? 37, 39. Can I squeeze them both on here? If that goes away. We're going to do that. Okay. All right. So, sorry about that. All right, gram formula mass of CaOH2. You go to your periodic table, look up the mass of Ca, look at the mass of O, look at the mass of H, add them up. Ca is 40 grams. Each oxygen is 16. 16 times 2, 32. Each H is 1. 1 times 1, or 1 plus 1, or 1 times 2 is 2. So 40 plus 32 plus 2, 74 grams per mole. I went a little fast because I kind of already have done this. This is why I picked some of these problems here. Just good review. Hopefully that makes sense. 39. Table F, which is least soluble. So if we go to table F, all right, here's our table F. Okay, least soluble. So now we're probably on this side. Here, let me do another one of these. All right, so, all right, we have AlPO4. So we'll do each one. AlPO4. All right, so we got to look up PO4. All right, so PO4 is right here. Aluminum is not one of the exceptions. So what does that mean? It means AlPO4 is solid, insoluble, because aluminum is not an exception. So I think number one's the answer, but let's see. LiSO4. I know Li is on group 1. In group 1. Group 1 ions, Li, always soluble. AQ, no exception. So anything with lithium will be soluble. So number 2 is not correct. CaOH2. Let's look up OH2, or OH minus. OH minus here. Ca is an exception. That means CaOH2 is actually soluble, so that's aqueous. So that's not correct for this question. AgC2H3O2. C2H3O2, this ion right here, I know is always soluble. And I know you probably don't have it memorized, but if you look here, right here, acetate, C2H3O2 minus, always soluble, no exception. So anything with that is soluble. So the answer is number 1, AlPO4. There it is, number 1. Okay. All right, and now we go back here. Sorry, guys, I lost the thing again. Should have just wrote it on paper. All right, 56 and then 64. 56, 64. Here we go. 56. Show numerical setup for calculating. All right. So, a sample of calcium carbonate, CaCO3, has a mass of 42.2 grams. Calcium carbonate has a gram formula mass, this is important, of 100. Show numerical setup, just a setup, for the number of moles in the sample of CaCO3. Okay, so we know there's 100 grams in 1 mole. We also know we have 42.2 grams. 42.2 grams. How many moles is that equivalent to? So this is my numerical setup. You can set it up differently, but this is how I teach it, right? So I do proportions. 100 grams over 1 mole equals 42.2 grams over X. We're solving for X, but that's it. I don't need an answer, so just the setup. And anyone who likes to do it differently, here I'll show you one thing. You can do 1 mole, and what you're going to do is you're going to multiply this by 1 over 42.2 grams. So that cancels. Oh, hold on. See, this is why I stick to the proportion, because I don't want to confuse you. But so anyway, this is how you do it. But those of you who want to see something different, like if you're going to take AP Chem, this sometimes makes sense doing dimensional analysis here. You would do 42.2 grams times 1 mole over 100. Get grams cancel, and you would get moles on top. So that would be your answer. But you don't need to do that. Forget that. This is how I taught it, so that's how we would do it on here. Okay. And what was it again? 64. Here we go. I believe it's a molarity problem. All right. So here we go. Determine the molarity of the acid. So I need moles over liters equals molarity, right? Molarity equals moles over liters. All right. During a titration, 10 milliliters of acetic acid is completely neutralized by adding 12.5 milliliters of 0.64 molar sodium hydroxide. Determine the molarity of the acid. Oh, no. You know what? I read this way too fast. I said, ooh, molarity problem. That's good for them to practice. This I have not taught yet. So I apologize, guys. Sorry. I went too quick assigning this one. Titrations are something we will get to down the road, like in May, but next month, I suppose. Or even early June, depending on what's going on and everything. But so you can't do this. So those of you who are interested, it's MAVA equals MBVB. This is on the back of the reference tables here. Right here, titration equation. And the way you would actually do this is you would say, okay, X for the MA, the VA is 10, the molarity of the base is 0.64, volume of the base 12.5. So 12.5 times 0.64 divided by 10 would give you the molarity of the acid. We haven't taught it. I haven't taught it, didn't learn it. So sorry, guys. My bad. So that's it. There's all the answers to the ones that were due. I'm going to kill the video here. It's already been long enough. Okay.